In the previous video, we talked about generally about the hypothesis testing concept. And that we need to have formed the null hypothesis. We need to have the alternative hypothesis. We need to have a measurement and observation, a test statistic. So from our data to go to a value is usually called statistic. For example, it can be the average mark, or it can be more complicated statistics like the t-statistic and so on. In some cases, the data itself is one observation, and in this case, this observation is actually the value that we use. So let's say that we have a value x in general, that we have a variable x that measures something from the data. So x is a function of the data. And then, having these components, we find or we calculate the distribution of x. So how x is distributed given the null hypothesis. So we have the probability of x given null. We have the density distribution of the x under the null hypothesis, and then depending what the h1 is, we compute the tail of this distribution accordingly. So for example, if the h1 is that this value is greater than expected, then if the distribution looks like that, and here is observation, we calculate this area. If the alternative hypothesis, the h1, says that this is smaller than expected, here is x again, we calculate this area, and if we say that it's different than expected, so here is greater, here is smaller or less, and if it's different than expected, then if this is what is expected, and here is our observation, then it means that our observation differs from what is expected by so much. So we calculate this area, and on the other side, this is also the same size as this one. So again, this one is more different than expected under the null. So both this area and this area express the probability to find an x that is more different than expected than what we have observed. In all these cases, this gray area here, this, or this together, is the p-value. Okay, so today we will apply this concept of p-value on what is called t-statistic and the t-test. So again, let's bring a biological setup here. Imagine that we have a gene, G1 let's say, and we have two groups of individuals. In group 1, we have measured the expression of G1 for healthy people. So the individuals, say 1, A2, up to say A10 are healthy, and we have some measurements of the expression value of G1 for these 10 individuals, let's say 10, 11.2, and so on and so forth, and here something like 7.5. And then we have another group of individuals, like individuals that are related to some disease. These are for example B1, B2. They don't need to be the same number, so let's say B9 here. And again we have some measurements like 9.1, 9.5, and so on. So what we assume here is that all these values, they come, and we use the symbol here, from a normal distribution with some mean and some standard deviation. And also these values are coming from another normal distribution with some mean and some other standard deviation. So the assumption here is that all these 10 values are realizations of this normal distribution, and these 9 values here are realization of this normal distribution. In other words, we have a normal distribution with some mean and some standard deviation, and we say that these values are coming from here. So for example, these are the 10 values, these 10 values here. And again here there is some other normal distribution with some that gives these 9 values. Our hypothesis, the null hypothesis, is that these two distributions are the same, or they have the same mean actually. So distribution A and distribution B now, under this assumption, these values and these values would be the realizations of the same distribution. And whatever difference they have, for example, their average values might be different than the average values of B, is just a stochastic thing. Just happened. So if the null hypothesis holds, then in principle the disease does not affect the expression level of the genes, or vice versa, the difference expression level of the gene does not cause the disease. So there is no relationship, there is no any relation between the expression level and the state of the individuals, if these A and B are the same. Now H1 in this case might be, for example, that the expression level of A is greater than the expression level of B. Of course, we might have other H1s like A smaller than B, or simply that A is different than B. The null hypothesis, the alternative hypothesis, the H1, depends purely on researcher's question, what is interesting for researcher to know. And set a priori the analysis. So we should not do the analysis and then see the results and decide, okay, this is comfortable for us. We should set the H1 before the analysis. Okay, now we have the null, we have the alternative, and we need somehow to summarize all these values into a single value. Now this is not very difficult because we can define a statistic called t, calculated in this way. You can check Wikipedia that this is correct. Or better to check with a t-test. Let's see, t-test maybe it's better. This one is the formula. It's fine, it's correct. Now this means that all these 19 values, 10 values from here and 9 values from here, will end up to a single t value. Let's call it t0 value. T observation. So our t observation is, let's say, I will put a random number here, 1.58. So if I will use all these values and do the calculations according to this formula here, then I will get this number. Okay, I have the H0, I have the H1, I have my calculation, and what I need to have more is how this t, how this random variable is distributed when the null holds true. So I need the probability of the t given the H0. So when in reality there is no difference between the two groups, when these distributions are the same, then what is the distribution of t? Now this can be calculated mathematically, and actually R and Python and all these programming languages know about it. And let's say that it's a distribution that looks like that. Here will be 0. So here is when in reality this mu1, here is better not to say, wait, I will put, here is the average of 1 minus the average of 2. And here is not the distributions standard deviation, but it's the samples. Not to be confused with these parameters here. Okay. So this is when mu1 equals to mu2. So it's a distribution that's around 0, and my t value So this is the distribution of t, and my t value, let's say that it's somewhere here, this is 1.58. And since my alternative hypothesis that a is greater than b, a greater than b it means that this value will become more positive. So I want to test how possible is to have such a high value of t, or even greater than this, when the null holds. In other words, I want to calculate the probability of these events here. And this probability will be the p-value for this alternative hypothesis. Okay, we can go to R and also check it there. So I go to RStudio. Okay, I have an observation, let's call it T0, and this is the 1.58. We know how to calculate it. I can even actually make the original values, make up some original values, like the values of the group alpha, let's say that's from a normal distribution. With mean, I don't know how many, let's say 10 values. Just make up some vector here. So these values represent the first group, these values represent the second group, and let's calculate the t-statistic. It's very easy in R. I will use a function my t-test, my test, and then it will be t-test or t.test, how is it? Yeah, t.test x equals to xa, y equals to xb. I just care about the t-statistic itself, so I don't want to make a test here, so I will use t-statistic. Oops, I must, maybe it's just t, don't remember now. Yep, let's find out the help. Okay, it's called the test. We need the return value. Maybe it's just statistic, yeah. So 0.49, not 1.58, but 0.49. Now the p-value associated with that is the following. We need the alternative hypothesis, and this is a greater. And let's see what else we need. Var equals, usually we put false here. We don't have any reason to believe that the var is equal between the two groups. So if I run this, then I get that the t-statistic is 0.49 as we said previously, and the p-value associated with this t-statistic is 0.3167. This degrees of freedom here, the df, is a parameter of this distribution and is associated with the sample size of each of the two samples. The fact that we have a p-value which is rather large means that we don't believe statistically that the means of the two distributions, the first that gives rise to this data and the second that gives rise to this data, are different. In other words, we don't have the statistical power actually to demonstrate that these are different, even though in reality actually the means of the two distributions are actually different. Now let's make the experiment in a bit different way to demonstrate how this t-statistic is distributed when the null is true. So let's say that when the null is true, these two distributions are the same. Now here I have different parameters. I will just use some other values close to these ones to make samples that come from the same distribution. So for example, if x1 is R norm 10, I will put 18 and I will put a variance, I don't know, 1.5 here or 2, and x2 is not totally correct what I'm doing, but I'm going to demonstrate 9 values, 18 and 2. Now these distributions are the same. And in this case, for example, a realization of the t-statistic would be the following. Here I will write x1 and x2. For example, I get a t-statistic value of 0.16, which is a bit smaller than what I got the previous time. But this t-statistic here definitely comes from the null hypothesis. Okay. Since it comes from the null hypothesis, I can repeat this many times to get realizations of t from the null hypothesis. I can do it like with a for loop. So let's say that I want to repeat it 1000 times for I in, I need a parenthesis here, for I so I'm going to repeat this thing and then get a statistic here and then save the statistic. So this is my t, for example, and then append it in another vector. So my t is here, will be an empty vector. Wait, this is probably wrong code. It's like Python code. Yeah, okay, sure. Like this. It's like that. Okay, now all these my t's, if I print them out, all of them are coming from this calculation here, which means that these two distributions are the same, which means that each t here is derived from the null hypothesis. It's derived from a hypothesis where x1 values and x2 values both are obtained from the same distribution. Okay, so I can easily now make a density plot or a histogram plot or whatever. Let's say plot density my t's looks like this. This is an approximation of this t distribution when the null is true. I can easily also put to see how many where my observation stands. So my t0, for example, my t0 is this one, t0, it's this value. Okay, so I can make here, for example, AB line vision equals to t0, color equals blue, and line width equals 2. So this is my observation, and this area here will approximately be the p-value, because my alternative hypothesis is to observe something greater than my observation. Okay, an approximation of this is just to say my t's greater or equal to t0, and I make a sum of this, and divide by the length of my t's, and this is approximately the p-value. And if you remember, the p-value is approximately the same number. So how I got the p-value here in this way? Here I ask, okay, these my t's are coming from the null distribution because they have been generated under a scenario where x1 and x2 are coming from the same distribution. Okay, so I ask, this one is a vector of true and false, and is true whenever a value from my t's is greater or equal to t0. Now in R, the true is transformed to 1 and the false to 0, so I can sum them up and find actually how many 1s I have. How many 1s I have means how many of these values of this vector are greater or equal to t0. And then I divide this by all the values in the my t's, and this approximates probability to find the value from my t's that is greater or equal to t0. And this is actually the definition of p-value, approximately here. So this is how I can test hypotheses with a t-test. Of course, we don't need to do all this repetition here because R knows this theoretical distribution and immediately can calculate here the p-value itself. Okay, that's all.